Okay, let's just get started and see if maybe it'll work later. So thanks a lot for the invitation to come. I always enjoy these holography kind of conferences. And today I'm going to try to tell you about these three ideas. And my background is very much in the same spirit as Frank's background. I want to start from some completely well-defined regulated lattice model, something like this spin chain here, where I have a local Hamiltonian, just like the Hamiltonian that Frank had. And crucially, I have a finite dimensional Hilbert space. So, this is in some ways very far from Lorentz invariant field theory. There's no Lorentz invariance. But on the other hand, it's completely precise. So this is a great advantage because you can put it on a computer, for example, and simulate. But to try to make contact with field theory, I'm going to ask only questions about low energy physics. So this is not the only kind of question you can ask experimentally, but it's an interesting subset which can make contact with field theory statements. Okay. And in particular, one possible thing that can happen is that some systems of interacting particles can actually secretly be theories of quantum gravity. This is what Maltasena told us. And here's a kind of cartoon. The field theory, or the UV of the field theory, lives on the boundary. That's this red. And inside the blue is the quantum gravity, or really the UV of the field theory lives here. And what I want to convince you is that this structure, this immersion phenomenon, from my perspective, is intimately tied to the way entanglement is organized in quantum matter. Okay, and so the framework that I'm going to think about is just to try to add these two things together. I want to take an RG picture and add entanglement into the mix and see what happens. So first I want to convince you that this picture is sort of a useful picture for thinking about the physics. And I want to do that by showing you a concrete computation where we can compute everything and find very precise agreement with actual numerical data. And then I want to use the intuition that I built in that setting to say something more speculative about the way that entanglement and normalization can combine to give you a certain kind of state or picture of the state, and then tell you how that's connected to holography and some more recent thoughts. Okay, so first, entanglement. So this is a caricature of experimentally realizable conditions. You can have low temperatures, you can have large samples, and you can reach equilibrium in solid-state systems. And so a natural limit to think about is the limit of ground states, that is zero temperature states, and a thermodynamic limit. So again, this is not the only kind of question you can ask, but it's a natural limiting question that's experimentally accessible, more or less. And so I'm thinking about ground states. I have a wave function, and just as Frank was saying, there's an important conceptual question here about how to think about this wave function. If I have a bunch of spins, n spins, then in principle this wave function is 2 to the n complex numbers. But this is extremely wrong way to think, because no one ever measures all these 2 to the n numbers. Most of the physics is insensitive to the details of these 2 to the n numbers. And so what I want to advocate instead is that you should think of, Frank showed you one way to think about wave functions in terms of these tensor networks. I'm going to show you another way, which is also related to tensor networks, but which you can also think of as a state viewed as a process. So a state is defined by the process by which I construct it from something simple, like an unentangled state. And in fact, this process is going to be a renormalization group process, where I build the state up scale by scale. Here's just precisely what I'm going to talk about. I have the same setup, even the same letters as Frank. So A and B. I'm going to always imagine the whole system is in a pure state. And so then I have this entanglement entropy and also the generalization called the Rényi entropy, which for our purposes is more or less the same thing. And I want to compute the entanglement entropy of A with B, which measures roughly speaking, how many singlets they share. And I want to use this information to say something useful about what the wave function looks like. Okay. So here's the zeroth order question is, well, how does the entanglement entropy depend on the size? And the analogous thermodynamic question is, or statement is that the thermal entropy is extensive in the system size. And so for gap states, what one typically finds, or almost always finds, is that the entropy scales, the entanglement entropy scales as the boundary or the area of the region. So here little d is the spatial dimension. So here I've drawn you a 2D picture. And the rough cartoon, the linear size is L, the rough cartoon is that I have some singlets which cross the boundary. And each of these singlets gives me 1 bit of entanglement, 1 log 2. And singlets which are just outside in B or just inside in A don't give you any entanglement. So this is a kind of rough sketch of what entanglement might look like. And this is, again, very similar to the picture that Frank was drawing before. But if you look more generally, you can look as a function of dimension as a function of whether it's gapped or gapless, and you find an interesting table, which looks like this. So here I show you the entropy, whether it's gapped or gapless in one dimension or more than one dimension. And if you want to have an example in mind, just think about Dirac fermions, some very simple physical system, which are either gapped or gapless in one or two and more dimensions, right? And you find that, as a function of the spatial dimension, the linear size, the correlation length, and some UV cutoff, that you have a sort of interesting table here. So area laws are obeyed in higher dimensions for gap systems, but also for gapless. And in one dimension, the area law is obeyed, but in one dimension, gapless systems violate it slightly with this log. And so later, I'm going to show you how to understand this table in this kind of scaling picture. But for now, let me just say that this table exists. Okay, and we can kind of reproduce this. There are a lot of checks with field theory, and you can check on a lattice, and this table there's a lot of evidence which goes into this table now. But now I want to switch gears a little bit and say, there's some scaling structure, but I want to try to say something really quantitative and precise about a particular system to convince you that this picture of entanglement and renormalization is a useful picture to have in your head. So what are the system I'm going to consider? I'm going to make the system as gapless as I possibly can. So critical points are already gapless, but Fermi surfaces are even more gapless. They have much more thermal entropy at low temperature. So I take this Dirac cone, and I'm going to fill it up. I'm going to add a chemical potential. So I fill up some states in K space. And what I want to show you is that if you follow the RG to low energies, that if you focus on the low energy degrees of freedom of this state, then you can compute entanglement properties very efficiently. So what does the low energy physics look like? Well, so here's my filled Fermi C, gamma. The white outside is empty fermion states, and the boundary, called the Fermi surface, is the boundary which separates empty states from filled states. And the low energy excitations of this surface, of this system, are just corresponding to taking particles inside and putting them just outside, right? Or equivalently to shape deformations of the Fermi surface. These excitations cause very little energy in the limit that you only move the particle slightly outside. And these are the low energy degrees of freedom. So first, let's understand something about the thermal entropy. So I say that these degrees of freedom are kind of quasi-one-dimensional. And the reason why that is because this Fermi surface is a contour of equal energy, right? And so the difference in energy between the K state and the sort of reference energy, which is the energy of the Fermi surface, this chemical potential mu, only depends on the perpendicular displacement, right? The parallel to the Fermi surface normal. So it kind of looks like I have a bunch of one-dimensional fermions which are propagating radially, and I have a Fermi surface worth of these one-dimensional fermions which propagate radially. And this immediately gives you a simple cartoon for what the thermal entropy is that you learn in any solid-state physics course. If I have turn on some finite temperature, I have a little thermal cloud of excitations. And this width of this thermal cloud in K space is roughly T over VF, just dimensional analysis. And every K state in this thermal cloud is uncertain. The fermion there is not sure if it wants to be empty or filled. It has equal probability of both. And so I get one bit of entropy for every point in this thermal cloud. And so you can just estimate the size. There's a factor of Kf for the perimeter, and then this delta K parallel. And that gives you an entropy which scales like this. So this is the standard way to guess the entropy of a Fermi surface. And this is very different from the scaling of a CFT, for example. It has one fewer power of T. So there are many more gapless excitations in this case than relative to a CFT. So what about entanglement? Well, this is also very easy to guess. I told you before on the table that gapless systems in 1D have a log L. And I told you on the previous slide that you can think about the Fermi surface as like a collection of one-dimensional gapless systems. So it's very natural to guess that you should have a log L, this 1D gapless answer, for every point on the Fermi surface. That seems like a reasonable guess. And indeed, I made the scaling argument more precise, and you can actually count in a very precise way the number of Fermi points, which is related to Kf, but also to the linear size, because if I have a region like this, the maximum wavelength that I can resolve is related to the total size of the region. If I have waves longer than that, I can't tell them apart because they look the same. So there's some sort of minimum cutoff in K space, which is related to 1 over L. That's why this appears here. And you get precisely this formula. And in fact, there's an even more precise conjecture. And now it's actually proven, but it was a conjecture at the time. that there's a very nice formula for the coefficient of this L log L term in 2 dimensions, which has a nice geometrical form as an integral over the Fermi surface boundary, so the Fermi surface here, and the real space boundary here. And this formula also comes out of the scaling analysis that I gave. And in fact, you can generalize it, so you can generalize it to include Rényi index here, and you can say something more precise about what you mean by this length. What exactly should I put, the total length or some other length, and so you can make that more precise as well. But I don't want to tell you in the details, I just want to say, okay, there's some formulas you can write down, which I don't expect you to digest. But at the end of the day, you can find this L log L, the leading term. You can find oscillating terms associated with Friedel oscillations in a Fermi surface. You can generalize the finite temperature. But I can distill these formulas down at 0 temperature into one simple expression for the entropy of, let's say, a disk as a function of the radius of the disk at 0 temperature in terms of these parameters. And what I can predict is A1, A3, A4, A5, and A6. The only thing which is unknown is A2. Everything else I can predict from the low energy theory. And so here is some actual data. I plot Rényi entropy over the perimeter of the region for a disk of radius L in 2 dimensions. And these are various Rényi indices. So this is the entanglement entropy here. This is the second Rényi entropy, and the third, and the fourth, and the fifth. And there are, in fact, 2 curves here. There's a dashed curve and a solid curve. But the point is just that they totally agree. And since I'm plotting S over L, the only thing I'm adjusting is the height of this curve. So all the wiggles and the overall dependence on L is given by the theory. So the point is just that this is a very gapless system. There's a lot of low energy degrees of freedom. It's not anything like a topological state, but we can still, by focusing on the low energy degrees of freedom, perfectly capture the entanglement in a very precise way. And in fact, we can do even better than that. We can actually also look at interactions. So here, this parameter Rs, so I'm plotting the same thing, S2 now, just the second Rényi entropy versus now log L. And this parameter Rs is basically measures how big the potential energy is relative to the kinetic energy. And you see that even when the potential energy is roughly the same as the kinetic energy, the black curve, which is the free fermion result, and the blue curve, which is the interacting fermion result, basically completely agree, more or less. And in fact, if you crank up the interactions even more, all the way as high as Rs of 20, the main thing which happens is that the curve shifts up, which is just a shift of the non-universal area law term. There's also some effect observed in the numerics where the slope, which is the coefficient of the log L term, changes. This is not predicted by the theory, and we don't actually know what this is. Maybe this be some numerical artifact. But I would say, at least for interactions that are as big as the kinetic energy, which is already quite high, we understand very well how to compute the entanglement of this interacting, gapless, complicated many-body system using this RT language. Yeah, so what this is a variation calculation. They take some fermion wave function and do Jastrow, and you can do various things. Yeah. So this is technically not the exactly right answer, but it's still showing that interactions don't do much.
Brian, how do you measure the potential energy?
Well, so I mean, there's just a Hamiltonian. I didn't tell you what the Hamiltonian was, but like it's Coulomb Hamiltonian.
Just use Coulomb.
So this is like basically this RS is the density. So it's a simulation with there's no lattice here actually. It's just a sort of standard free fermions with a quadratic band with Coulomb interaction. And so that's how you figure out. You just put the density, and then that tells you the potential energy.
Is there Friedel oscillation for entanglement and truth tensor?
No, there's not. Yeah, for various reasons, it vanishes when you go to the entanglement limit. And actually, I'm happy to talk about this later. I can explain why this is, but let me not do it right now.
If you go to this Wigner crystallization lattice.
Yeah, if you go to the Wigner crystal, then of course it will oscillate. If you break the translation invariance in the ground state, it'll definitely oscillate. Okay. In fact, let me just mention also that you can actually write down rigorously solvable models. Again, here's the model. Don't worry about the details. If you care, you can look in my paper or ask me. But in this model, it's a model of fermions coupled to some spin degrees of freedom, some other degrees of freedom. It's like a 2-component model. And actually, in this model, you can rigorously prove that the entropy breaks up into 2 terms. One is, so the total entropy is like a fermionic part plus a spin part, which you can compute from the decoupled models. And this model has the nice feature that you can, for example, rigorously prove that this L log L term is not affected by the quasi-particle residue. So that's the overlap of the bare electron with the physical electron. There's some physical electronic quasi-particle. It has some finite probability to be found when you insert a bare electron into the system. And you can just prove in this model, which is not the most general Fermi liquid, but it's some subclass of all Fermi liquids, you can just prove rigorously, completely rigorously, that it doesn't affect the entanglement. And again, actually, if you look at the guts of this model, it works because we're working in a certain kind of coarse-grained limit. So again, RG is giving us some computational power, some ability to prove exact things.
This statement applies to all the Rayleigh entropy too?
Yes, and even at finite temperature. So it's actually extremely powerful for many purposes.
Can you mind apply it?
Yeah.
You have here an exact solution for the Gauss state?
Yes.
Yeah.
Well, I mean,
I didn't.
so technically what I should say is that each of these pieces may be hard to compute.
Okay.
Like this may be a critical theory, but I know the entropy is exactly additive. So for example, even if this is the critical Ising model, I know it doesn't have a log L term in it. And so this log L is unmodified. Yeah.
A really naive question. I mean, is the lesson here that for the Fermi systems, almost all the entropy is just in the Fermi minus signs? So would you expect similar robustness to interactions for Galpos-Bose systems? What's the main takeaway lesson?
Yeah, I mean, I think, well, the takeaway lesson from this is that these universal terms are really universal, and that's what doesn't change. Now, for the Bose system, the leading entanglement is going to be the area law, and that will probably be much more sensitive to details. So the fermions are special in that they have this extra amount of entanglement, and that is also universal and very insensitive to the details. So that's like, I guess, the lesson is really the universal terms are universal.
So how do you define SF and S sigma?
Well, actually, so you take this model. In this model, you just turn the coupling. So you just, like, this couples the fermions to the spins in some way. If you just delete this thing here, so there's like a decoupled, there's a version of the model which is a decoupled spin fermion model where there's no coupling. There's a precise way to say this, and you just compute the entropies of those decoupled models. So in this model, it would just be the entropy of fermions hopping in some band, and the entropy of these sigma particles with this coupling to the fermions turned off. But there's a precise way to specify what.
So you compute SF, S sigma, and the decoupled limit.
Yeah, it's a property of the decoupled model.
Some of them doesn't depend on interaction.
And some of them does not depend on interaction for this class of models. Okay. So now I want to sort of move to the original motivation and say, okay, so what? Okay, so showed you can calculate these things. I hopefully convinced you that at least in this one example, and this is a particularly nice example, but there are others which we can work with, where if you combine entanglement and normalization into some kind of common framework, you can say a lot about numerical data. So what I want to do is use this intuition to say something useful, conceptually useful about quantum matter and holography. And I'm going to go back to this idea that we should build ground states scale by scale in terms of their entanglement. And so from now on, I'm going to drain the Fermi sea again and go back to zero density, and in fact back to one dimension, but replace my spins with just blobs. So if you like, you can think of these as some large n matrix degrees of freedom, or whatever you want, right? But I assume the Hamiltonian is local. And I want to ask this question: how to think about the wave function. So here's one very interesting way to think, which combines these ideas of entanglement and renormalization. So I start with a spin chain here, my blobs on the previous slide, at the UV scale, the microscopic scale. And I want to coarse grain. I want to flow to low energy to focus on the low energy degrees of freedom. But I can't do that directly because there's a lot of short range entanglement, right? These degrees of freedom may have a lot of short range correlations, which have nothing to do with long range physics, but which are nevertheless present. And if I try to coarse grain without dealing with these short range correlations, then I'm going to introduce a lot of uncertainty into the state because these degrees of freedom are strongly correlated, right? They're strongly tied together. So I want to decouple them first, and then I can throw them away, right? That's kind of the picture. So that's the job of this blue person, this disentangler. You can think of this disentangler as I want to sort of coarse grain this two party block here into one state, but there's short-range correlations between this block and its neighboring blocks. So I want to remove those correlations, and then I want to coarse grain. So you don't need to worry about the details of this picture too much. There are many ways to implement this scheme, but this is just one RG scheme if you like. But the rough idea is I want to remove short-range entanglement and then coarse grain. Right? So I reduce the number of sites, number of degrees of freedom. And so I can actually implement this by saying I have a state, and I apply some transformation to that state, which is a 2-to-1 RG scheme, which takes the UV state and produces a renormalized state on fewer degrees of freedom. And then the idea is, okay, I have a lattice here again. I can repeat this procedure. I can remove short-range entanglement between these coarser degrees of freedom, and I can again coarse grain. And in fact, you have a kind of procedure. The procedure would be to do this removal of entanglement and coarse graining until you have no entanglement left. And so you can introduce a scale R, which is like a length scale. So R equals epsilon is the lattice. R goes to infinity is the UV. And I have a scheme. Let's say I take k sites to one site. So in this way, R grows in this fashion. That's a power of k. And I just imagine starting in the UV, and I apply one layer of the circuit, which takes me to a slightly more coarse-grained system, and then another circuit, and then another circuit, and so on, until no entanglement remains. And no entanglement remains when either I reach essentially the correlation length, so the idea that modulo topological structures, once I reach the correlation length, everything's decoupled, so there's no entanglement left, or when the whole system shrinks to nothing, right? So if I have a finite-sized gapless system and I renormalize long enough, I'll eventually shrink the whole system to a single site, right? So I stop the RG once either the entanglement is gone because it's a finite correlation length, or because I've shrunk the entire system to nothing if the thing is gapless. So if I have an infinite system, the circuit would just go on forever because there's an infinite number of degrees of freedom. So you end up with a picture like this. This is a 2-to-1 scheme again. So I sort of have some UV lattice, and then I renormalize, and I renormalize again, and I renormalize again, and each time depleting the number of degrees of freedom. And you can summarize all this, you can abstract all the things I told you about, all these tensors in this nice graph. And this graph is useful because, as Frank was saying before, if you have one of these, this is just another kind of these tensor networks. And so there's a general fact that whenever you have these tensor networks, the amount of entanglement that you can produce, say from this red dot to this red dot, so how entangled this region is with everything outside in the world, that's bounded by the minimal number of bonds you have to cut in the network to isolate the red region from the rest of the world. And so, for example, you could cut all these bonds here, right? But that's very bad because that's a lot of bonds you're cutting. There's no reason to cut so many bonds. You can actually cut much fewer bonds if you use the fact that you're reducing the degrees of freedom a lot as you go down. So here, in fact, you can cut a logarithmic number of bonds by going down, by coarse graining, and you have much less entanglement generated. Right? So this minimal curve, if you like, in this discrete graph geometry bounds the amount of entanglement that can be produced by this state for this region, this red region. So this is a rigorous bound. It's a more or less trivial bound. But actually, if you do numerics, then you find that this bound is actually typically saturated, or this bound controls the actual entropy that you add. So this kind of minimal curve in this discrete graph geometry actually tells you what the entanglement is, not just bounding it. And in fact, you can actually prove this. There's another formulation, which I won't talk about, of this kind of entanglement renormalization program, actually, which Frank initiated, where you can actually prove in one dimension rigorously, or semi-rigorously, that indeed you add a fixed amount of entanglement at every RG step. So the proposal is that this is a graph. It has a geometry which is hierarchical. It looks a lot like the geometry of ADS. And so the rough proposal is that you should interpret this graph as some discrete version of ADS, and that the usual rules of holographic duality may have some analogy here. But let me just make a brief aside and say that it's, in some ways, it's not really so exotic. You don't have to worry about holographic stuff. It's just another kind of tensor network. It's a variational state. You can start with general tensors. You can minimize them. You can change them to find a minimum energy, and that gives you a wave function. Right? So this is just a variational ansatz which encodes the RG structure of your system. But I want to say it's more than that. I want to say it really has something to do with holography. And so let's go on. So here's a kind of picture of I promised you a scaling argument for this entanglement picture, this entanglement table I told you before. So here's a kind of scaling picture. So let's imagine here's my green region I want to compute the entanglement of. And at the UV scale, I have some singlets which cross the boundary. That's these guys. So I get a little bit of entanglement. And then I renormalize the system. So I reduce it by a factor of 2, let's say. And I get a little bit more entanglement. And I reduce it by a factor of 2, and I get a little bit more entanglement. And so on until the region shrinks to nothing, or until I run out of entanglement. And so you see, actually, I'm going to get a logarithmic in region size number of singlets I've counted here. And so the entropy will be proportional to the logarithm of the linear size. And you can draw similar pictures in 2 dimensions. I have some area with a bunch of short-range singlets, then a coarse-grained area with some more short-range singlets, and another coarse-grained area, and I keep shrinking things down again until I reach a state where either the region has shrunk to nothing or I have no entanglement. And this is all encapsulated in this sort of simple heuristic expression for the entropy that you add, kind of an integral expression which captures these discrete sums. And indeed, if you just make this IR cutoff equal to the minimum of the size of the green region and the correlation length, then you indeed get this table I showed you on the previous slide. And of course, if you know something about holographic computations of entanglement entropy, this also looks very similar to the kind of formulas you get in that context. You can do other things. Another interesting quantity to consider is the mutual information, which measures correlations. And you see in that case that there's an interesting kind of phase transition which occurs. If I have 2 regions and I'm looking at the correlations between them, so I'm computing this quantity, the entropy of just region 1, just region 2, and the entropy of the combination, subtracting them, then there are 2 kind of behaviors you can expect. Either if the regions are close together compared to their linear size, then what happens is as you renormalize, they merge together first, and then only later shrink to nothing. Versus the limit where they're very far apart, they first merge to the lattice scale, and then only later come together, right? So there's a qualitative difference between these 2 situations. And in fact, you find, indeed, that the mutual information behaves very differently. Here, it's a very large quantity. Here, it's really controlled by just a few low-dimension operators in a long-distance limit. Yeah.
That kind of physics need large N, or you think?
It depends. It depends on what you have. So, like, if you have a vector model, then because there's a large number of primary fields growing with n, then this will actually be proportional to n also, because there's a lot of. But if you have a matrix model, so if there's no n parameter, then which you'll just find that this is very large. Like this will diverge as these regions are brought together, and this will decay very rapidly with the dimension of the lowest primary field which can contribute. So it's not as sharp as at large n, where there's a large n matrix model where this will be order 1, this will be order n squared. But there is still some qualitative crossover.
Can you see in this formalism that it does become sharper in a matrix model?
Yes, you can actually. I'll comment on that very briefly at the end. Yeah. And speaking of operators, you can also do operators. I won't go into the details here, but this is just to show you that. So here's some actual data, numerical data. You can use this variational state to find the ground state of a quantum Ising model. This is the work that Guy Vidal and Glenn Evenbley did. And you can find operators such that when you renormalize them, so you apply one layer of the circuit, the renormalized operator is proportional to itself, right? So that's like a scaling operator. When I coarse grain by a certain factor, I get the same operator back, but up to a factor, which is related to the conformal dimension. And so actually, just using the properties of these tensors that form this network, you can compute the dimensions of the operators. And this is at the critical points. And you see, you get 0, 1/8, 1, the usual values. And this is, of course, everything is easy in 1D, but still, it's a proof of principle that this kind of technology can actually be useful for solving real problems. Yeah.
The procedure. So seems like this procedure breaks the translation symmetry.
The network itself does break translation, but what you find is that at the end of the state is translation invariant.
The network.
The network, the explicit network connectivity breaks it. I mean, it favors certain ways of coarse graining things. But the resulting state at the end of the day is translation invariant when you minimize everything.
You mean when you minimize everything, the whole network, you say, in the end is translation.
If you just look at if you look at the actual state, like look at correlations in the actual physical state that's produced by the network, then that state will have translation invariant correlations.
Sorry, the state is the whole network, right?
Well, what I'm trying to distinguish is the network. So you have the network, and the network produces a state, right? You contract the network, and I'm saying that state looks like actually has translation invariant correlations, even though the network you contracted is not exactly translation invariant. That's what I'm saying. Does that answer your question? It doesn't have to be, but we find empirically, that it's the case. And in fact, for some models, you can actually prove analytically that you can rewire the network in various ways without changing anything. So this lack of translation variance is kind of a fake thing. So you have actually a nice picture where these operators kind of follow trajectories, if you like, through the network. I can renormalize the operator. If it's a scaling operator, it returns to itself, but now it's at one layer down. So I can kind of move operators through the network. They follow these kind of paths. And the idea is I would move two operators to where they're next to each other, and then I would get some kind of OPE coefficient. I would do some short distance physics to figure out what the correlation function is. So I could, for example, have two operators which come together, they merge to form another operator, and then that operator goes lower down to meet a third operator, and they combine in some way to produce a correlation. And just by tracking all these links in this discrete geometry, you can reproduce formulas like this that come from CFDs. So this is the picture that I want to advocate. You have some emergent direction associated with RG flow in this graph. There's a quasi-geometric formula for the entanglement. Yeah.
We know that these operator at the endpoints on the implant are twisted, right?
No, this is just any correlation function. I'm not necessarily
I'm not
talking
talking
about
about
just twist fields.
entanglement.
So you can also do twist fields. That's a different story. This is like these operators I was showing you before, just the epsilon or something like that.
A sigma are twist field in the sigma.
Yeah. So these sigmas require you to do something a little extra. You need to have strings, like branch cuts, basically. So there's a way to do non-local operators too.
Yeah, there is also the Wigner string, right?
Yes, exactly. So I totally didn't tell you any of the details of that, but it can be put into this framework. Yeah. So let's just think about local spin, like the energy would obey something like this. So yeah, so there's this quasi-geometric formula for the entanglements, a quasi-geometric formula for correlators, at least a picture. It's local at the level of the graph, and the geometry, the graph depends on the state. So you do different states, you get different graphs. So I want to call this some kind of emergent holographic space. And okay, everyone here knows holography, so I'm going to just quickly skip this and say a few things about the recent applications. So the point is just that, okay, so I have this picture again. This extra scale in holography is also associated with the RG scale. And so you can do various checks. You can say, well, if I have a geometry, does it end if I have a gap system? And indeed it does, whereas it goes on forever if I have a gapless system. Similarly, the entanglements, the Ryutaki-Nagy formula says entanglement is some kind of minimal curve, at least in the large N storm coupling limit. So that also kind of matches the picture we had from this network. Mutual information, I think Matt may talk more about this, I don't know, has a similar picture where, as you increase the distance, eventually the minimal surface will be the two disconnected guys instead of the connected guy. So you produce this kind of phase transition. And you can also look at correlators, and at least in some heavy probe limits, these correlators also follow trajectories or geodesics through the geometry.
There's still a bit of intuitive, right? What you really have is a network,
Yes.
a connection. And to go from a network to a geometry, right,
Yes.
you have to have a sense of a metric and so forth.
Yes.
So how to think about it?
Well, I mean, you have this discrete graph geometry. You have a taxi cab. You have some kind of metric on this graph, and that's fine. But the question is how to really see if things are smooth. But it's also not clear to what extent things should be smooth for the Ising model, for example. So if you have like a large n-matrix model, then maybe things are smooth. So what I would say is actually what happens is these tensors have a lot more structure when you're looking at a large and only a couple of matrix models than they do in the Ising model. And that the smoothness is hidden in the ability to rewire the network and in the structure of the tensors.
I mean, would you go so far that eventually it would look like kind of a dynamical triangulation?
Yeah, I think that's
Like a
exactly the picture.
and you coarse grain it and it turns into
It's a triangulation with a lot of extra data on the links. But indeed, I think that's the basic picture. Yeah. Okay, so, okay, so there's a slogan here. Entanglement is the fabric of space-time, which I like. People are throwing out slogans these days a lot, so I have a slogan too. But yeah, so there's a proposal, okay, that this is one way to approach understanding this holographic geometry from a completely well-defined, computationally useful framework for thinking about ground states and dynamics in many-body systems. That's the idea. And there's been a lot of additional work, some by people in this room, including things like symmetry. I talked about in some of my papers black hole-like objects that occur at finite temperature. You ask me about it if you want to know. You can include Wilson lines if you're doing gauge theory. So there's a lot of stuff that you can play with here.
How do you get a GTT into
Well, that's hard to do. What you can track is the way that the Hamiltonian renormalizes as a function of scale. So like Hamiltonian is one of these guys, so you can put it in the scaling limit, you see that it's just, 2 or whatever. But actually, if you put it in finite temperature, what you find is that it starts to go to 0 faster than that. So it's like the Hamiltonian is vanishing, or you're approaching infinite temperature, which is sort of the same thing. But you can't really explicitly get GTT yet in this framework.
Brad, the kind of correlation function you talk about is all equal space correlation function, or you can do different time?
So this is all wave functions. So the basic picture I presented here is all equal time correlators.
But can you do different time?
In principle, yeah, but it's more complicated. You need to, you can try to do something, but this is still a work in progress. So let me not try to say too much about it. Yeah.
So you had a statement that the geometry is determined by the state, but actually it seems that you make a choice of network. I mean, I can see it terminates depending on the state, depending on the temperature, but that seems to be the only aspect of the geometry that you presented that depends on the state.
Well, I presented a particular network. I mean, what you might want to think is, I want to somehow let the network vary as well, or consider a very general network where some of the links can be turned off if they're not being useful to the system. So I think there's a implementation question about how to actually vary the network in a nice way. But I think conceptually one can think about changing the connectivity or having some kind of general framework and then turning links off as they're not used, for example. Yeah.
Related to Huang's question, is there a good way to describe excited states in this?
You can describe excited states, but it's related to changing what happens in the bulk, right? So if you put in a different state or change some of these low energy, some of these tensors, and you can get different states. Yeah.
Correlations is some kind of entanglement, or how it's related to
Is the correlations.
correlations?
Oh, well, I mean, it's basically just this picture I gave you. You put two operators in, and they get renormalized until they collide, and then there's some short distance calculation you need to do. So you have a density matrix of some local degrees of freedom and two operators, and you compute. Basically, it's an OPE coefficient in the field theory language, and so that's the kind of calculation you do. And that's not exactly the same thing as computing the entanglement. Yeah, it's conceptually different. Yeah. Yeah.
I just wanted to add something about this question of whether it's the network or the state.
Yeah.
It's not quite right that you might fix the network, and in some sense that might be reflect the topology if you want your spacetime. But when you said that it's the number of bonds you cut, I mean that was kind of a bit of a simplification, right? Because when you cut a bond, you have to ask what state was there, and depending on it could be a state where there's almost no entropy in that bond.
Yeah.
So the actual value you'll get from that calculation is not just the number of bonds, because from that picture you say, oh, it doesn't matter what the state was, it's just once I have the network I know my entanglement entries. That's not true. You first have to find your state, and your entanglement entry will definitely depend.
I completely agree.
So in that sense, the metric is not dictated by the network. You have to know your state, if assuming this correspondence exists. it will depend. The metric will depend on the state.
Yeah. So the statement about this number of bonds cut is only a bound. And for simple choice, where I know how to choose the network right, then indeed this bound is sort of giving you the full answer because each bond is contributing the same amount. But you're absolutely right. In a general setting, some bonds may contribute nothing, others may contribute a lot. So it depends on the details of the tensors. Yeah.
So if you have some generic time evolving state, would you have a sort of preferred way of generating this network, or once you pick?
Well, so there's a lot of choices you can make. One choice is I take a state at each time, and I try to remove as much entanglement as possible at each scale, and then just keep doing this and see what I get. So that's one algorithm for, let's say, I try to reduce the mutual information between density matrices as much as possible.
And that's well defined.
That's a well-defined algorithm. Whether that corresponds to something holographically, I don't know. Yeah.
Do you have any idea what kind of equation your metric satisfies? For instance, it should not be an Einstein equation for most field theories.
Yeah. We have some idea, but not complete idea. Yeah, you can try to study perturbations in this thing and like how they move through the network. And like the Laplacian on this graph will have the same low-lying modes as the Laplacian in an anti-de Sitter space. So that you can look at the graph Laplacian and study in the usual way. So there's some sense in which it looks roughly like the wave equation on ADS, but yeah, it's still very open what exactly the equation satisfied by these tensors is. Yeah. Okay, I'm over time, so let me just say, oh yeah, this is funny. So I was at this conference on quantum complexity, and everyone was presenting theorems, so I wanted to have a theorem too. So here's my theorem. I have a craziness axis. And Ising model is down here, not crazy, because it occurs in the real world, and n equals 4 is crazy. And I want to tell you, entanglement normalization, I claim is that it works in both limits. This is by explicit calculation. This is because it's holographic. And so by the intermediate value theorem, it must work. That's my theorem. Let me skip this and just say, so let me just briefly comment about this strong coupling large N issue. So what I think is true is that this local RG circuit is a general feature of local quantum matter, but some special things should emerge at strong coupling and large N. So for example, you should have this sparse spectrum of operator dimensions. The geometry should be less fluctuating in some sense. You get these large N phase transitions we were talking about. And so actually in this paper from 2012, I showed some preliminary results along these directions, where if you assume these tensors are strongly mixing in a certain precise sense, then indeed the spectrum of operator dimensions is very sparse. You only have a few low-lying operators, and everything else is pushed to very high operator dimension. So it's sort of similar to some kind of scrambling picture. And at the same time, when this fact happens, when you have very few low-lying operators, what happens is these tensors tend to add entanglement for sure to the state. So it's like a transformation which almost always adds entanglement and adds a definite amount of entanglement. And that looks like some kind of classical non-fluctuating geometry. Yeah, let me just also mention, because I never talked about this, you can try to do dynamics in a different setting. This is actually work we did with Mark and his student Connor and Nima, who are at UBC. And so we tried to say, suppose I had this large N limit and I want to do dynamics in this system. You can kind of set up a model where I have some very primitive model where I have sites with some density of states. And this density of states I'm going to choose in some way related to the large N density of states, for example. So I'm really just trying to take this picture over here and look at some dynamical properties based on the expected structure of these tensors or what you might think would happen. And eventually I want to make contact with dynamics in mirrors, but this is just a simpler version where I have some classical problem. I have a master equation for energy to move around on this lattice, and I have transition rates which are specified by this density of states and some other information. And what you find actually very, very simply is that depending on the way the energy spectrum goes with energy, you find either diffusive, so the energy spreads out if the log of rho goes slower than the energy. It's static if it's Hagedorn-like, if it goes like linear in the energy, and it clumps if it's faster than E, right? And so what we were trying to say is this is a very simple, very, very simple model where you just have density of states. It's classical. It's stochastic. There's a master equation. You just have energy conservation, a density of states, and some transition rates. And nevertheless, you find that long timescales emerge. And the idea is these long timescales are somehow related to black holes, right? Because you have black holes, you collide energy, forms a black hole, and it just sits there, which is really weird, right? And then it slowly radiates energy. And in fact, these features can be seen in the numerics. So I encourage you to take a look at this paper if you're interested in this kind of stuff. And like I said, the ultimate goal is really to make contact with this entanglement picture and dynamics in large N. So we can have start to get a really complete picture of how we start from the simple many-body system and we build up a complete picture of statics and dynamics in the holographic setting. So with that, let me just say thank you. There's two messages. One is that everything is unified because of entanglement. So you can talk about all this stuff in one language, and that language is a combination of these two ideas. So with that, thank you.
So you said you can reproduce this formula, say, for the 3-point correlator in CFT. I mean, how far can you push that? How much can you reproduce about the structure of correlators in CFTs?
So you can look at 4-point functions, for example, which are not constrained by conformal invariance. And actually I had a picture like, in various limits, you can reproduce the fact that, in various limits you get this factorization, right? So if like two of them are close, then they form a third, and then they're farther away. So you can do things like this, but you can also see the exchange of different primary fields. So like if I have them, if they're sort of all equally far apart, then I can bring them together and I can see that, different primary fields could exchange. So I don't have anything concrete to say, but there is something you can do. The network is telling you something. And I don't know what that is, but yeah, you can, it would be interesting to understand this.
Yeah, a kind of curiosity question. So most of these redux are 1D, right? And we know very interesting wave functions, be the Alsace constant.
Yes.
To what extent is the tensor network variational state and be Alsace the same thing?
I actually don't know about the beta unsought state itself, but certainly you can do this for the spin half chain, and you can get the physics out right. So in that sense, I think it probably works. I don't know about the details of.
Very interesting.
Yeah, that's a good thing. So like in other contexts in higher dimensions, there are states for which you can show this is the exact wave function, this Mira, like these topological states can be exactly cast in this framework. So there are interesting wave functions for which this is the exact answer, or they have exact representations. Sorry?
The Fermi gas.
The Fermi gas is difficult because it doesn't obey the area law. So actually you have to generalize this network to include the fermions, and that can be done. We've done that along with Giuffre and Glenn, but it's a more complicated story.
Have you explored the possibility of different rates of renormalization at different depths in the network, or different rates at different points along the chain?
Not really. Yeah, I'm aware this is interesting, but I haven't thought about it that much. There's like a lot of. One thing I can say is there's a lot of gauge freedom here. The way you choose the tensors and what percentage of the tensors you choose, and that may be somehow associated with diffeomorphism structure in the bulk. But yeah, I haven't really looked very closely at this inhomogeneous scaling. I mean, one thing I have looked at is if you like anisotropy. So like if you have like a magnetic field, and so it breaks up into so the system for some reason becomes very anisotropic. So it could start with an anisotropic system and then flow in the infrared to like decoupled chains, for example. And that actually, I've done that kind of thing in this network.
The reason I asked was that if one allowed oneself to change the rate of RG along the chain and at different depths, then you could insist that the information content on each node were the same, and then you'd be sure that your bond cutting really gave you the entanglement. That would.
Yeah,
the construction would be the entanglement, not even a band.
Yeah, that may be interesting actually. There's a continuum version of this where you can do things like this much more easily, and I think actually that would be interesting to look at in that context.
Because both the definition of math and this one is, you would need either one of these things if you want to reproduce sort of the bulk space-time more generally, because you can't just have the fixed links to the
Exactly, yeah.
Also, it would induce a dependence of the geometry on the
On the
time
yeah,
of
the state
evolution of the
has to be
state. So
different.
you
Yes.
if you use that.
Yeah.
So what's the meaning of the square on the right-hand side?
Oh. Well, actually the power is dimension dependent. So in one dimension, this is the right answer because curves are the minimal surfaces.
Sorry, why there's a square there? I still don't understand.
Oh, it's just for notational cuteness. No, so this equation is exactly true in one dimension,
So why it's true in one dimension?
and in higher because there you have curves.
Take the square root.
Yeah, take the square root. So I just squared an equation that was true, so it's still true in one dimension. But in higher dimensions, you need to put a power. You need to compute the area, so it's ds to some power.
So if you're interested in, dynamical systems, things that evolve in time, and you're interested in relativistic systems,
Yeah.
it's natural to ask if there's any interesting kind of, covariant, time-dependent generalization to this formula. Is there anything to say about that? Even I take something that worked with a Euclidean path integral, but had a t direction in it.
Yeah, the Euclidean path integral is more doable. I mean, I can do tensor networks for path integrals.
That makes sense.
That makes sense. It's different from this because I'm not describing a state. I'm describing this path integral. But yeah, that can be done in principle, or that can be done. I've done it.
What does it look like? What is it?
Well, I mean, it's similar. You can still have this RG structure, but like now you just do time as well. So think about just think about Euclidean. Suppose I want to write the Gibbs state of some Euclidean, some stat mech model, right? And I can do this kind of RG picture for that. But I just interpret one of the directions as time. So I have like time sites. I have time and I have space and I have lattice. I have Euclidean lattice.
You're still describing entanglement by these links?
No, it's not necessarily describing entanglement.
Or you're just doing RG with interaction?
Yeah, some generalized, just RG in usual kind of Euclidean path integral framework. So it's not obviously related to entanglement. Yeah, it's some kind of integral. It's just correlation. Yeah.
Last question.
You started your talk drawing an analogy between entanglement and entropy, area versus volume law, and then you essentially went on defining entanglement as the von Neumann entropy, or at least that was the impression I got from.
That's definitely how I define entanglement. Yeah.
So, but the von Neumann entropy brought to finite temperature develops a volume term. So, do you have an idea of how all this extends to low but non-zero temperatures?
Yes.
What do you have to do to
So instead of a pure state, you have a mixed state now. So I have a two-sided circuit, which comes in, and at the bottom, I'm going to get some mixed state. So I remove all the entanglement, I remove all the correlations, but instead of having a pure state, which gives me no entanglement, I have a mixed state. I have a bunch of decoupled mixed states. So then I'll have an extensive contribution based on how big my system is from all these mixed states. And this is actually can be thought of as like the black hole horizon in some sense. So yeah, that's a good question. But yeah, you can